Good morning, everyone. Welcome to the class of 745. Today, the subject of the class will be differential line theory. Last Saturday, I went outside to a mountain and there was a lot of cold rains. But today, the weather is becoming warmer and warmer. I love spring coming. So in April, I'm expecting beautiful flowers on this campus. Let me start the class. You remember that in the previous classes, we was talking about transmission line theory. We was discussing the transmission line impedance and source impedance and termination impedance. And also, depending on the dielectric constant, we have different phase velocity and we have length of a transmission line. By having a transmission line, we was able to send very high-speed digital signal with minimal loss and distortions, with minimal time delays. But I would like to say that impedance control is really difficult. If we have impedance discontinuities, we will suffer reflections that will cause multiple reflections and time delays and dingings, and it will result in EMI and crosstalk issues. Why do we have difficulty of transmission line impedance continuities? Because our interconnection has three-dimensional structures. Because sometimes our transmitter and receivers are on the same plane inside the chip, but in a lot of cases, we have to send digital signal from a chip to chip. Then it has to go through from chip to package PCB, and sometimes we have to go through cables. Because of that, impedance in three-dimensional structures such as package, PCB, and connector, and cables, all these has three-dimensional structures, and it is very difficult to maintain constant impedance. Another difficulty is the ground. In order to construct transmission line, we always have to have ground plane underneath the signal line. But in three-dimensional structures, it is very difficult to maintain continuous ground plane. If we have any discontinuities at the ground plane, it will cause impedance discontinuities, and that will create the reflections. In addition to that, we at really high-speed digital signaling, we have to think about crosstalk issues and the high-frequency loss effect, and we're gonna talk about those things in April classes. But at this moment, let's think about this impedance discontinuities and the reflections. One of the smart way to avoid this impedance discontinuities and ground discontinuities is the differential line interconnections. In the conventional single and signaling scheme, we have a single signal line on the top of ground plane. But in the differential line scheme, on the top of ground plane, we are using two wires, two interconnections. And we're gonna have a virtual ground plane between the two lines. Because of that, we have less impedance discontinuities. But the price, the cost of differential signaling scheme is that because we are having two lines, number one and number two, it means we have more interconnections. That means it will take more areas and more power consumption. And today I'm going to talk more about the basics of differential line theory, what is advantages and what are the requirements. And on Wednesday class, I'm going to talk about the applications of this differential line theory. And we're gonna show you some real schematic of transmitters and receivers and common mode and differential modes. To start the basic theory of differential line theory, I'm going to start with odd mode and even mode. Odd mode is related to differential mode. Odd mode is connected to common mode. And usually differential mode is very good for high-speed signaling. Common mode is causing EMI, usually EMI problems. This differential signaling scheme is a three-metal system. That means we have one ground metal, two metal, three metal. So in the single-end transmission line, if we have two metal system, we have only single mode. But in three metal system, we have two different modes of propagation. One is being called as odd mode, and the other one is even mode. Odd mode is different, in other words, differential mode, and even mode is common mode. Odd mode is very good to maintain the ground plane and impedance. However, even mode is a source of EMI. So in order to send really high-speed signals in these three metal systems, we really have to keep the differential mode and we have to minimize the common mode. As I mentioned before, if we use the odd mode and differential mode, basically odd mode is a microwave society terminology, and differential mode is more likely circuit society terminology, but basically the same. And in order to minimize the reflections and EMI, we have to use odd mode. And interesting thing is that if we are using three metal system, we're gonna have odd mode and even mode. Odd mode has different impedance and phase velocity, and even mode has different mode and velocity. In other words, I would say that if you are sending differential mode signals through three metal transmission line system, we're gonna have differential mode impedance and common mode impedance. In other words, odd mode impedance and even mode impedance are different. In the single-end transmission line, we have only single 50 ohm line impedance and single propagation speed. And propagation speed was depending on the dielectric materials, dielectric constant. But interesting thing is that in the three metal system, we have odd mode impedance and even mode impedance, and odd mode propagation velocity are different from even mode propagation velocity. Let's assume that you have 10 metal system, then you're gonna have very large number of modes. So that is a little bit difficult compared to single-end transmission line. So in the case of odd mode, odd mode voltage is applied to metal 1 on the left metal. However, on the opposite polarity, minus odd mode voltage will be applied to the adjacent metal. Of course, we have ground reference plane. Sometimes, even though we are not having this ground reference plane, but still we can send odd mode. So in this blue line is showing the electric field distribution. Because we have two metal system and one at the cross section, we can apply still the static electromagnetic field theory and circuit theory. Then if we apply the positive odd mode voltage in a metal and the negative voltage on the other, so polarity is different, magnitude is the same. These two metal is becoming a pair, or we usually call it as a differential pair. Then electric field will start from a positive metal, voltage metal to negative metal. At the edge, is gonna be a straight line, but on the other side, it's gonna be a fringing field. And because of symmetry between metal 1 and metal 2, we're gonna have a virtual ground plane. This is becoming virtual ground plane. In the single metal case, we have metal, but ground plane, this was the ground plane. But however, if we are sending odd mode, we're gonna construct a virtual ground plane which will be placed at the middle of between the two metal systems. And this electric field will be vertical to this metal plane. That is the boundary condition of electric field. And I remember you were studying electromagnetic field theory at the sophomore class, and you may remember that at the boundary condition if you apply the boundary condition of electric field, you may remember that electric will be at the junction, at the ground plane, it will be vertical. Of course, this surface of metal plane, always this electric field should be vertical to the metal surface. That is the condition of metal boundary condition. So because we have this virtual ground plane, it is not a physical ground plane. It is a virtual ground plane. So even though you do not have any metal ground plane, if you are sending high-speed digital signals through this two metal system with the differential signaling means then one voltage applied to one metal, the opposite metal will be applied to adjacent metal, and both are generated at the same time and propagating at the same time together and received at the receiver at the same time. If they are propagating it with a different speed, it will cause some problem. We're gonna talk about that on Wednesday class. And because you remember that if we have ground plane, virtual ground plane, and metal system, we're gonna have impedance. Impedance will be the ratio of current wave and voltage wave. In this case, we're gonna have odd mode current at one metal, and odd opposite metal will be induced at the adjacent metal. And by having the relationship between this odd mode voltage and current, we can define, this is actually wave, and we can define odd mode impedance. That is called odd mode impedance. Meanwhile, let's talk about even mode. In the even mode case, same voltage wave will be applied at both metals, and then because this metal and this metal has the same voltage, actually electric field will be directed from top metal to ground metal. Of course, at this surface of the metal, it should be perpendicular. So here also, we're gonna have even mode even mode current will be induced at the top metal. Same polarity even mode current will be induced on the top metal, and opposite even mode current will be induced at the bottom metal surface. Because of the relationship between even mode current wave and voltage wave, we can define even mode impedance and even mode impedance here as well. That is being called as even mode impedance. Because Maxwell equation is linear equation, we can apply the superposition principle. So in any cases, if you are sending voltage and current wave in these three metal systems, we can decompose that voltage and current wave into odd mode and even mode. Even mode is average voltage, and odd mode is the symmetry, oppositely symmetry voltage. We can decompose that, and each odd mode, decomposed odd mode and even mode will have different impedance. So generation will be different, even mode and odd mode. Generation will be different, propagation will be different, and reflections will be different. So in the three metal systems, you have to deal with those two different kind of electromagnetic waves. That is a little bit difficult compared to single-ended transmission line. Let's also talk about phase velocity. In odd mode case, more field is exposed to air. And so because of the distribution of some field to the air and the dielectric, we're gonna have some effective dielectric constant. And because of that, we're gonna have a little bit different phase velocity in odd mode. And however, in even mode case, most of fields are inside dielectric material. And so it's gonna be affected by dielectric constant of this material, and we're gonna have different even mode. Now, let's think about odd mode and even mode phase velocity. In odd mode case, more field is exposed to air, so it will travel a little bit faster than even mode. Even mode is traveling mostly through the dielectric. If you have dielectric constant, and it will be, the propagation speed will be reduced. In odd mode case, fields are more confined between the metal to the ground, virtual ground, and virtual grounds are very close to each other. So usually odd mode impedance is smaller than single line impedance, and even mode impedance is larger. So basically, open mode and even odd mode is related to differential mode, and by definition, we're gonna talk about that later. Or differential mode impedance is twice of the odd mode impedance, and common mode impedance half of the even mode impedance. Usually, common odd mode impedance is around 50 ohm. That's why differential mode impedance is usually 100 ohm. Usually, even mode impedance is near the 50 ohm. Because of that, common mode impedance is usually less than about 25 ohm. This is very starting overview of the class today and Wednesday. Chang Seon, are you there? Can you speak to me? Okay, Kim Tae-woo, are you there? 박동열?
예, 교수님 혹시 들리십니까?
네, what is your name?
박동열입니다.
Okay, would you summarize this slide for me? It is a little bit of introduction of differential line theory. I was talking about impedance, phase velocity, field distribution. Would you tell us a little bit about this slide?
예, 그 기존에 저희가 싱글핸드 트랜스미션을 배웠을 때는 그 G0를 그냥 가정하고 이렇게 모든 문제를 풀었었습니다. 근데 이제
네.
실제로 3D 저희가 실제로 트랜스미션을 만들 때는 3D 스트럭처를 가지고 있고 또한 그 각각의 이제 모든 시그널들이 비아 패키지, PCB, 커넥터, 케이블 뭐 이런 식으로 다양한 컴포넌트를 통과를 하면서 지제로 컨트롤하기를 어려워졌고
네.
또한 그라운드 컨트롤도 어려워졌습니다. 그래서 저희가 이제 3메탈 시스템인 3메탈 시스템은 오드 모드, 이븐 모드를 배워서 그때 지제로를 컨트롤하기 어려운 그런 것들을 해결하는 방법에 대해 배우는 과정 중에 있고 그때 이제 오드 모드 이제 3메탈 시스템으로서 시그널을 달리 입력할 수 있기 때문에 오드 모드라 이븐 모드가 있습니다. 그렇게
네.
돼서 오드 모드에서는 이제 필드 분포를 보게 되면 그 메탈 사이에 버추얼 그라운드가 있어서 그 버추얼 그라운드에서 이 필드가 이렇게 이 필드가 이렇게 중간에 볼티지가 제로인 지점을 지나게 되고 그리고 이분 모드에서는 실질적으로 리턴 커런트 패스가 이제 그라운드로만 모두 형성이 되는 것을 볼 수가 있습니다. 그리고 이제 벨로시티나 이제 그 G0를 보게 되면 오드 모드가 살짝 더 이제 속도가 빠른 것을 알 수가 있고 또한 그 G0 또한 실제적으로 이분 모드보다는 낮은 것을 볼 수가 있습니다.
훌륭합니다. 오늘 몇 번 좀 도움을 청하겠습니다.
네.
Yeah. So, in three metal system, there are some advantages and disadvantages. But difficulty of that is we have two different impedance and two different phase velocities. For example, if we are designing termination resistance, we have to consider two different modes. If ideally, odd mode and differential modes are what we really want, but in many cases, on Wednesday, I'm going to talk about common mode and even mode will be generated. For example, if the line lengths are different or driver size are different, or because of parasitic, sometimes we are unintentionally generating the common mode. Thank you. You are a very nice student. Let's move on to the next slide. Yeah, now still it is this is the introduction of the class. Let's think about advantage. Motivation is really important. Theory is later on, it will be coming on. Let's think about a case where we are sending this signal, high-speed digital signal from, let's assume this is four-layer PCB. Sometimes we have CPU is placed on the top and DRAM maybe on the bottom. And sometimes because of the placement and routing, we have to go through the via. And then return current has to come back. And sometimes it is a circuit level or sometimes it is a wave level. Return current has come back. But usually this plane is designed for power and this plane is designed for ground, and power and ground is not connected. So this return current has to go through this parasitic return current. This is a kind of displacement current, and it has to be connected to the return current on the power plane. And so because of these discontinuities, we have some impedance reflection problem because this parasitic return current path will create some impedance discontinuities. Because of that, there will be a lot of reflections. So because of that, we have return current discontinuities and impedance discontinuity. Sometimes this parasitic current will induce the resonances depending on the size of this PCB, and it's gonna be an EMI source. However, if we are using the differential signaling scheme, we're gonna have virtual ground plane between the two wires. In this section is gonna be traces, and in this area, the differential pair will be a form of traces, but here will be a via pairs. If we are using two interconnection in parallel with the differential excitation. You have the differential signal excitation. You're gonna form a virtual ground plane, virtual ground plane. So it is much, if you have a virtual ground plane, by controlling the distance between your wire to the virtual ground plane, you can achieve more convenient differential mode impedance and odd mode impedance. And then you can minimize the reflection. So by having differential signaling scheme, you're gonna have virtual ground plane, and you will have it is easier to achieve impedance continuities, and because of that, we're gonna have less EMI and crosstalk issues. But the penalty of this interconnection is because the interconnection number will become twice compared to the single-end signaling scheme. Another example, this is another example of advantage of odd mode and differential mode. In these days, because we have large number of I/O, large number of I/O, because we have to use the BGA or something like area type of interconnection. Wire bonding is using the wire, but BGA type of packaging is the area type. So we have much larger number of interconnections. It is a kind of periphery, so one-dimensional array. But if we are using the BGA, we're gonna have much larger area type of interconnection. So basically, we can increase the number of interconnection. Why do we have to increase the number of interconnection? Because we wanna increase the bandwidth between our device to between other devices, like from GPU to DRAM. We wanna maximize data bandwidth to achieve high-speed machine learning calculations or metaverse calculations. We need very large and high bandwidth between GPU and memory. Other cases, possibly, yeah. And another possible case is that because of power. Power interconnection usually have inductance, and to minimize the voltage drop and simultaneous switching noise, we have to minimize the inductance. One way to do that is to increase the power interconnection. Also, we want to provide the return current path, always to be able to send a high-speed digital signal. We have to maintain the ground. So that means that we have to have very low impedance ground. In order to reduce the ground impedance, we have to increase the number of interconnection for ground. Because of that, number of interconnection will be 100 times or million times more interconnection will be needed in 10 years. So we cannot use this wire bond type anymore, but still some high-speed interconnection such as the optical fiber communication drivers and receivers, and still some of them are still using wire bonding. And in the single-end wire bonding case, if this is a wire and if this is a ground, there are so high distance from wire to ground, and this is becoming very high impedance, and this will cause the reflections. So one way to avoid that is we are using the differential signaling scheme. One positive wave will be applied to one wire, and negative voltage will be applied to the adjacent wire, and that will be propagating at the speed of light. And then we're gonna develop a virtual ground plane between the two wires. Because of this virtual ground plane, we can control the impedance and phase velocity, and we're gonna have less EMI and less crosstalk. So there might be many different type of three-dimensional structures when we are transiting. We have transitioned from chip level to probably PCB level or package level, we're gonna have some such an three-dimensional interconnection, then a ground is really difficult to maintain. In this case, there are some distance between the wire to ground plane. In those cases, also those ground plane has to be connected to on-chip ground plane as well as the PCB ground plane. That is also very difficult. Some case it is going through the wire. So it is very difficult to maintain the virtual ground plane. And in this case, by having differential signaling scheme, we can achieve the virtual ground plane. And because of that, we can have very good continuity of impedance. This is another advantage of odd mode and differential mode. Now, let's take a look at a little bit closer to the field distribution of odd mode. And I was talking about in the previous slide, but let me repeat it again. Positive current, actually this is wave voltage and current, and voltage wave and current wave will have a same phase velocity and same propagation velocity. And the relationship between odd mode and odd mode voltage and current is defined by odd mode impedance. And this image current voltage will appear at actually ground, and the image current will appear at the virtual ground plane. On the left side, image current will appear on the left side, and also another opposite image current will appear on the right side of this virtual plane. Because those are amplitude are opposite each other, actually it is becoming addition of both virtual current will become zero. So mathematically, it will be okay to assume we have image current at the virtual ground plane. And opposite polarity, but this odd mode voltage to appear at the adjacent metal will propagate with the same speed. It will propagate with the same velocity of odd mode propagation velocities, but voltage level and current polarity will be opposite. At this junction of virtual ground plane, electric field will be perpendicular each other. Probably some charge will appear on the left side and minus charge will appear on the right side. But this is actually virtual, they will cancel each other. And so we can assume this is the virtual ground plane. And this voltage on line 1, line P and line N, we have opposite polarity and current has opposite polarities. In electromagnetic field theory, we are saying that it is image current. So when you are designing differential signaling scheme, you should be able to imagine this voltage wave and current wave and image voltage and image current and virtual plane, and also field distribution. You should be able to imagine this field distribution as well. In this case, this is a case of electric field. Now let's talk about magnetic field. Because I0 wave will propagate into the G direction and opposite image current will propagate into the minus G direction. And because of the Maxwell theory and Ampere's law, which you were covered in electromagnetic class in your sophomore years, we're gonna have magnetic field across or surrounding this metal. Because we have opposite current, opposite direction of magnetic field will be induced. At the virtual ground plane, this magnetic field and this magnetic field will be in the same direction. And because of that, and boundary condition, here is the boundary condition, boundary vector is in this direction, and here boundary vector is this direction. Because of that, we will induce the surface current at this virtual ground plane. This will be -0. This is the virtual ground plane. And also we're gonna induce the image current at this virtual ground plane. This current will cancel each other. Also, I would like to remind you that this is becoming metal boundary condition of magnetic field. So this H field will be the tangential, parallel, so tangential to the metal plane. And very strong magnetic field will appear at the center, and at the edge, magnetic field will be small. So I would like you to be able to imagine electric field distribution and magnetic field distributions of differential mode. And of course, if you are thinking about common mode, and this is the odd mode, and this is the even mode, and depending on common mode and differential mode, field distribution will be different. Because of the field distribution is different, you have different odd mode impedance and even mode impedance and the propagation velocities. This is the physical electromagnetic field physical picture of a differential mode with respect to electric field and magnetic field. 동열, are you still there?
예, 교수님.
조금 반복되기는 하지만 이 디퍼런셜 모드와 코먼 모드가 맨날 헷갈리기도 하고 그래요. 그랬는데 어쨌든 이 개념을 좀 잡기 위해서는 필드 분포를 조금 이렇게 알면 자신 있게 그 버추얼 그라운드 플레인을 얘기할 수 있는데요. 한번 전기장 한번 살짝 짧게 설명해 봐 주실래요? 어떤 모양을 갖고 있는지?
예, 이제 플러스로 그 전압이 유계되고 이제 마이너스 전압이 유계되는 그 두 개의 메탈 사이에서 이제 실질적으로 그 벌추얼 그라운드가 형성이 되게 됩니다. 이때 저희가 벌추얼 그라운드를 볼 때 이 필드는 경계 조건에 의해서 그 버티컬한 성분만 가지게 돼서 다음과 같이 그 버티컬한 성분만을 가지면서 이렇게 벌추얼 그라운드를 통과하는 형상을 가지게 되고 또 이것이 벌추얼 그라운드를 가지기 때문에 저희가 전자기획 때 배웠던 영상법에 의해서 그 이미지너리 커런트가 흐르는 것처럼 좀 생각을 할 수 있다라고 좀 말씀을 해주셨습니다.
맞습니다. 맞습니다. 또 한번 자기장 한번 얘기해 볼까요?
예. 자기장도 똑같이 이제 저희가 전자계학 때 배웠던 것부터 차근차근 잘 설명해 주셔서 제가 들었던 바로는 이제 H 필드 자체가 바운더리 컨디션에 의해서 탄젠셜 성분만 생기게 돼서 벌추얼 그라운드 사이에서는 벌티컬한 성분이 생기지 않고 다음과 같이 위쪽 또는 아래쪽으로만 흐르는 탄젠셜한 성분만 생기게 되고 또 이러한 것이 두 개의 메탈 사이에서는 그 좀 강한 자기장을 형성을 하게 되지만 다 같은 다이렉션으로 강한 자기장 형성이 되게 되지만 이 메탈 그 바깥쪽으로 가게 되면 갈수록 자기장이 약해지는 현상을 가지는 것을 확인을 하였습니다.
네, 훌륭하십니다. 학부 수업 전자기를 아주 잘 배우셨네요. 예, 예. 그래서 우리가 이제 시그널링 디퍼런셜 할 때는 뭐 디지털 시그널링 막 브로드밴드 한데 필드 티어리까지 막 왔다 갔다 하는 게 좀 그렇긴 한데 그래도 이 전체가 학부 때 배운 과목하고 다 연결하면 재밌을 것 같아서 이렇게 하고 있습니다. 근데 지금 디퍼런셜 모드 전압이나 전류가 지금 그림에서는 이제 스테이틱하게 그렸지만 사실은 빛의 속도로 날아가고 있는 것이다라는 말씀을 드리겠습니다. 빛의 속도로 날아가니까 반사가 있을 거고 뭐 우리가 싱글핸드에서 했었던 현상이 다 또 존재를 하는데 지금은 디퍼런셜 모드만 따지만 커먼 모드도 같이 존재하니까 두 개가 동시에 막 발생하고 전파되고 반사되고 뭐 그런 현상들이 있습니다. 그런 현상들을 정확하게 모르면 어떤 때 이제 본인이 생각해 본 것보다 이제 시스템 파형이 떨어져도 해석이 이제 어려워지게 되겠습니다. Now, let's talk about impedance first. What I would like to say is that this graph shows this. Let's assume this is uh, microstrip differential line scheme. We have ground plane. We have one line. Usually say it is a P line. We have N line here. We have virtual ground. And I would assume that we have W and S. Sometimes, in most cases, let's assume that we are designing differential line on PCB. Usually, direct constant is fixed, and the thickness is already fixed, and metal width is also usually fixed. So most cases, we are just controlling the space between the two lines. Please pay attention to this. If the space is very infinite, very long, that means two lines are really separated far away, that means single odd mode impedance is becoming just single line impedance, because the interaction between the two wire is almost neglectable. In this case, if the S space is really large, we have just two single end lines. That's why if space is becoming higher and higher, it is becoming 50 ohm. Let's assume single end line is 50 ohm and the two differential pair is separated far away, then we're gonna have 50 ohm. That's why this odd mode impedance is approaching to 50 ohm. But however, if these two line space is very close to each other, like very close to each other, major impedance that is controlling this impedance, odd mode impedance is distance from this line to the virtual ground. It is really very close to each other, then this odd mode impedance more dominant. You remember that impedance is square root L divided C. If the virtual ground plane is very close to each other, C is becoming higher. That's why odd mode impedance becoming smaller and smaller. That's why odd mode impedance is becoming smaller and smaller, like 30 ohm. So what I would like to emphasize at this moment is that odd mode impedance is a function of S. Of course, it's also a function of W and H, but in most cases, when we are designing PCB, what we are usually controlling is SS. And if S is becoming very small, odd mode impedance is becoming smaller and smaller. And if the space is becoming infinite, and then it's becoming single mode impedance 50 ohm. In a similar way, if the space is becoming smaller and smaller, even mode impedance, later we will talk about that even mode impedance, it is becoming 60 ohm. So separation is quite large if they are becoming closer and closer. So one mistake of beginning signal integrity engineer is that, let's assume you have a single line impedance 50 ohm. If they are very close to each other, they still assume differential mode impedance, odd mode impedance is 50 ohm and even mode impedance is 50 ohm. That's big mistake. If the two lines are very close to each other, we have big difference between the even mode and odd mode. So if you are not properly designing the terminations, in this case, you're gonna have severe reflections of even mode and odd mode. One meaning of this line is that we have odd mode is smaller than single mode impedance, and even mode is larger than single mode impedance. That is one meaning of this. And if space is becoming very, very small, means the two wires are placed very close to each other, then even mode impedance, odd mode impedance, the difference is becoming higher and higher. 그래서 여러분들이 라인 하나 임피던스 55ohm이라고 생각하고 열심히 설계했는데 라인들이 가까워지면 오드 모드, 이븐 모드 임피던스가 55ohm에서 벗어나기 시작해. 그러니까 인터커넥션을 많이 하기 위해서 space very close to each other, impedance of lines may be quite different from what you are thinking as single line impedance cases. 동열, thank you very much today. I will ask you to summarize this slide for me.
예, 교수님. 지금 여기서는 이제 다른 변수들도 있지만 실질적으로 저희가 트랜스미션 라인 설계를 할 때 위스랑 하이트 그리고 스페이싱이 있는데 이때 스페이싱을 변경해 가면서 오드 모드, 이븐 모드 임피던스를 본 상황입니다. 그래서 다이렉트리 컨스턴트랑 스페이싱 위스가 똑같다라고 생각을 했을 때 저희가 50ohm이라고 생각해서 만들었던 이 싱글 라인이 두 개의 스페이싱이 점점 가까워지면 가까워질수록 벌처럴 그라운드의 영향이 더 커져서 실질적으로 3메탈로 가게 되고, 그래서 실질적으로 오드 모드의 경우에는 임피던스가 낮은 형상을 가지게 되고 실제로 저희가 설계했던 것보다는 낮은 임피던스를 보이게 되고, 이븐 모드에서는 저희가 실제로 설계했던 것보다는 큰 임피던스를 가지는 것을 보일 수가 있습니다. 그래서 저희가 이제 주의를 해야 될 게 실질적으로 PCB를 설계할 때는 스페이싱이 좀 제한적이어서 어느 정도 가까워질 수밖에 없는데, 이때 만약에 메탈들이 가까이 있고 디퍼런셜 라인 스킴을 사용을 한다면 임피던스가 달라져서 리플렉션이 많이 일어날 수 있기 때문에 이런 것들을 조심해서 설계해야 된다라고 배웠습니다.
훌륭한 학생인데 박동현 학생 우리 랩으로 옮길 생각 없는지 나중에 나도 개인적으로 만나야 되겠다. 자, 그래서 여러분들이 이제 싱글 라인으로 55ohm이라고 했을 때 디퍼런셜 한다고 그냥 두 개 라인만 붙여놓으면 되는 게 아니라 그럼 임피던스가 줄어요. 오드 모드 임피던스가. 그래서 다시 또 조정해야 돼요. 디멘전을. 그런 얘기를 드리겠습니다. So this is the summary of so far of the class so far. We have two different impedance, two different propagation velocity, and two different field distributions. So sometimes when you are designing interconnections, you want to know what is the impedance. And there are many different ways to obtain this odd mode and even mode impedance. Is first equations. Because this structure is not perfectly symmetry, because you see, if you see up and down, so field distribution are really not perfectly symmetry. So equations are not easy to obtain, but there are some empirical equations. You can obtain that from textbooks or from internet. Also, sometimes in a book or papers, the impedance are listed as table. So sometimes you can obtain from graphs. For example, you can obtain this kind of graph to obtain the impedance and phase velocity and things. Also, you can do the measurement of your PCB. In most of the PCB companies, they are regularly check their PCB to measure the impedance. Their customers are asking to maintain certain single line impedance and differential line impedance. And of course, a PCB processor has certain variations. So they want to maintain the quality of their impedance, and they are how they verify that. And design state, you can use this kind of simulation method. And also you can use the 3D EM simulations, such as NCS and Maxwell's. You can calculate using numerical simulations, but sometimes you want to verification purpose, you can use the measurement. In the frequency domain, you can use the network analyzer. And in time domain, we can use TDR meters. But both of these measurements has some very hard to do that, because in order to measure, we have to use the probe. And probe itself has parasitics or cable effect. So it is really difficult to extract only a line effect. So I would say this measurement is also has certain limitations. So in order to obtain this odd mode and even mode impedance and phase velocities, you need very extreme expertise in the frequency domain measurement as well as in time domain measurement. I think most conventional way of to obtain this impedance and propagation is the 3D EM simulation. So if you wanna be a good I/O circuit designer or signal integrity designer, you should be able to do the circuit modeling and simulations. But in addition to that, you should be able to do the 3D EM simulations. From the 3D EM simulations, you can obtain the model or parameters, and these parameters will be injected into the circuit simulation to simulate the time domain waveform. But more difficult thing is that we have process variations such and also this impedance are depending on structures and dimensions and materials. And process variation is coming from material properties and dimensions, and that are mostly the responsibilities of PCB manufacturers. In addition to that, sometimes we have temperature effect. Some material properties are depending on the temperatures. So those are the difficult part of impedance and phase velocity control. So now I would like to talk about the design of differential signaling scheme. When so far I was briefly talking about the basic theory and field distributions of differential line interconnections. And now let's look at those issues with a different angle. And in most cases, we have to design these differential interconnections. And then we should design line impedance such as differential impedance and common mode impedance. Odd mode impedance is related to differential mode impedance, and even mode impedance is connected to common mode impedance. Also, you have to design propagation velocities and line length L. And also, you may have different length of differential mode, and you may have different length of this is not a physical length. This is more like electromagnetic propagation length. Sometimes common mode are going through some chassis and cable shears. So you may not know the actual length of the common mode. So you have to design this propagation length as well as the propagation velocity and the length. And because of that, you're gonna design different differential mode delay and common mode delay. Also, you probably on Wednesday, I'm going to talk about termination. So you have to also design the differential mode terminations and common mode terminations. And also source impedance of differential mode and common mode will be different. And also sometimes you may have ground plane, or to control the common mode, you have to design the ground plane. And also you have to, sometimes it is unavoidable to have this impedance discontinuities and deflections. And in those cases, how much discontinuities and deflections you're gonna accept, those are also design issues. And also one different thing is that depending on your interconnection design, sometimes a differential mode will be converted to common mode, and common mode will be converted to differential mode. And if you have some non-linearity element in your circuit or some imbalance of your circuit interconnections, you're gonna suffer some differential mode and common mode conversions. And those are, I think, the main design issue is depending on your design, delay and EMI and power consumption will be affected by compromising between delay, EMI, and power consumption. You have to design this all differential interconnections. Now let's spend some more minute to talk about the relationship between differential mode and odd mode. Please pay attention. Many times people are confused between the differential mode and odd mode. Odd mode is more likely microwave theory, very popular analysis method in microwave circuit theory, and differential mode is terminologies which are being used in circuit theory. Basically, those are same, very little different. Now we have odd mode voltage and current, and we have image plane. Odd mode impedance is the amplitude of odd mode voltage divided by odd mode current. This is actually wave voltage and wave current. And odd mode impedance like that, usually it is near the 50 ohm. However, differential mode is line to line impedance. So voltage is odd mode voltage, and so odd mode impedance is a definition of a voltage and current wave between the metal to virtual ground plane. But differential mode case, it is a line to line impedance. Actually, because it is there is another odd mode impedance is here and odd mode impedance here. It is a serial connection if we are considering line to line. That's why we have twice. If we are defining the voltage from a line to line, it is a twice of odd mode voltage, and image current is induced at the adjacent metal, and so image current is the same. So that's why it is becoming twice of odd mode impedance. So usually let's assume that odd mode impedance is 50 ohm and differential mode impedance is usually 100 ohm. But phase velocity is the same because field distribution doesn't change. Only the difference between differential mode and odd mode is the definition. Differential mode is the wave voltage and current ratio between the two lines, line 1 and line 2. But odd mode voltage and current impedance is definition between line 1 to virtual ground. So simply, you can assume that differential mode impedance is twice of the odd mode impedance. 동열 학생 한번 오드 모드와 디퍼런셜 모드를 한번 설명해 봐 주시겠습니까?
예, 교수님, 이제 오드 모드라는 터미놀로지는 마이크로웨이브 시어리에서 자주 사용하던 터미놀로지고, 디퍼런셜 모드는 서킷 시어리에서 자주 사용하는 터미놀로지인데, 두 개의 용어에 따라서 보는 이제 임피던스의 관점이 달라서 다음과 같이 임피던스의 차이가 있는 것을 확인을 하였습니다. 첫 번째로 오드 모드 같은 경우에는 메탈과 벌추얼 그라운드 사이에 있는 필드를 보기 때문에 다음과 같이 커런트랑 하나의 볼테지만의 이런 관계 수식으로 나타내지게 되는데, 디퍼런셜 모드 같은 경우에는 실질적으로 두 개의 라인 사이에서의 그런 임피던스를 보게 됩니다. 따라서 두 개의 라인 사이에서 유게되는 두 배의 볼테지와 그리고 하나 흐르는 커런트로 나눠지기 때문에 저희가 기존에 사용하던 오드 모드보단 2배의 큰 이런 임피던스가 보이게 됩니다. 하지만 하나 더 짚어주셨던 것이 두 개의 필드 분포는 똑같기 때문에 실질적으로 가는 벨로시티는 똑같다라고 말씀해 주셔서 이게 보는 관점에 따라 임피던스는 다르지만 실질적으로 그 웨이브가 이렇게 점송되는 속도는 같다라고 확인을 하였습니다.
박동현 학생 천재인 것 같아요. 천재인 것 같아요. 자, 그렇습니다. 디퍼런셜 모드와 오드 모드는 전자기적으로는 같은데 데피니션의 차이인데 오드 모드는 라인과 버추얼 그라운드 플레인 사이에 웨이브가 흘러갈 때 임피던스고 디퍼런셜 모드는 라인과 라인 사이에 그래서 버추얼 그라운드 플레인 입장에서 직렬과 직렬이기 때문에 2배가 돼서 보통 오드 모드 임피던스가 55ohm이면 디퍼런셜 모드는 105ohm으로 디파인이 되어 있습니다. 우리가 보통 이제 when we are applying this differential mode impedance, I think there are some cases such as PCI Express. PCI Express is usually used for computer-to-computer high-speed interconnection. USB is usually for computer and peripheral devices. HDMI is for connection between the display and maybe set-top box and computer. And also we may have a serial ATA. This is the storage network. All these applications, they have to really send high-speed digital signals. And because of that, they are using this differential signaling scheme. They have certain specification. And in their specifications, they are saying differential impedance is 100 ohm. When you read that specification, you have to imagine odd mode, and you have to imagine the virtual ground, and you have to imagine odd mode impedance is 50 ohm. Also, you have to remember that in these applications, you are supposed to control the differential mode. But in a lot of cases, unintentionally, you are designing, you are supposed to use the differential signaling, but sometimes common mode is generated. And how to control this common mode, that is also a big part of our interconnection design. And these are usually conducted through the ground, and it is not written on the textbook or specification. But when you are integrating your system with the RF communication system or automotive vehicles, because of this common mode, you may have a larger problem because your customers are requiring certain level of suppression of EMI. If you want to suppress EMI, you have to control the common mode, and then you have to design this interconnection to minimize the differential mode to common mode conversion. In order to do that, you really have to design the ground really well, including the virtual ground. Now, I would like to spend a little bit more time to talk about common mode and even mode. In the even mode, we do not have a virtual ground plane. Electric field will be like that. And so even mode impedance is this ratio of even mode voltage wave divided by even mode current wave. You remember that this is usually a little bit larger than the single mode impedance. Now, common mode definition is assuming that we are connecting these two metal, then current voltage is the same, but current is becoming twice because we have same current wave and same current wave, and image current will be induced at the ground plane. So current is twice, but voltage are same. So that's why common mode impedance is the half of the even mode impedance. 박동열 학생 한번 얘기해 볼래요? 커먼 모드와 이븐 모드의 차이를?
예, 교수님, 이제 이분 모드 같은 경우에는 실질적으로 저희가 넣는 이제 전류와 전압만이 보이게 되어서 다음과 같이 저희가 잘 아는 이제 전류 전압 관계의 수식으로만 보이게 되는데 이분 모드 같은 경우에는 어, 라인 페어와 그라운드 사이의 임피던스가 보이기 때문에 라인 페어로 보게 되면 이게 저희가 인간 전류가 이제 2배가 보이게 되고 전압은 똑같이 보이게 됩니다. 그래서 그렇게 됨으로써 저희가 이분 모드보다는 이제 이 커먼 모드는 이분 모드의 절반의 그런 임피던스가 보이는 것을 확인을 하였습니다.
네, 그렇습니다. 그래서 USB나 HDMI나 PCI 익스프레스 보면 커먼 모드 임피던스를 이제 정의하면 25ohm이라고 하는 이유가 요거를 두 개가 같은 메탈이니까 묶여져 있다고 보는 거예요. 웨이브 입장에서는 묶여져 있지 않은데 회로 입장에서는 묶여 있다라고 보는 거예요. 그러니까 그냥 전류는 2배고 전압은 같으니까 이게 이제 커먼 모드 임피던스는 반이 됩니다. 그래서 우리 다시 this is the summary of the class today. We have odd mode impedance and even mode impedance. Those are not same. We have odd mode impedance phase velocity and even mode phase velocity. By the definition of circuit theory and microtheory, differential mode impedance is twice of odd mode impedance. Its common mode is the half of even mode impedance. Now let me spend one more slide to you. This is also very important subject. Let's assume that you have two waves. One voltage wave is propagating at line, and another voltage is propagating along line 2. That can be decomposed to odd mode and even mode because of the superposition principle. So how are we doing that? Even mode is the average of this voltage wave and current wave, and even mode current is the average of current wave I1 and I2. But odd mode is the difference of these two voltage, and current is two different voltages. By having this definition, what we can do is we can analyze this signal using odd mode and even mode because we know impedance and propagation velocities. By having this voltage and even mode, odd mode, and at the end of analysis, you want to obtain V1 and V2, then by addition of odd and even mode, you can obtain the V1, and by adding even and odd mode current, you can obtain the current of 1. And voltage wave at 2, line 2 is the difference between even and odd mode, and current wave at line 2 is the even and odd mode. What I'm saying is that this is more odd mode and even mode is based on more symmetry. Field has more symmetry and voltage more symmetry. Because of that, you have uniform odd mode impedance and even mode impedance, something like that. So we can apply the electromagnetic theory, but at the end, if you want to know what is voltage V1 and V2, you can use this relationship, and V1 is addition of voltage of even and odd mode voltage. V2 is the even and odd mode difference. That is the beauty of this differential mode and common mode analysis. 동열, sorry, I would like to ask you one more time.
예, 이제 저희가 실질적으로 설계를 할 때는 각 라인별로의 볼테지를 구하는 게 좀 목표가 될 수도 있습니다. 근데
네.
이제 저희가 이제 보낼 때 디퍼런셜 앤 모드 또는 커먼 모드로 이제 시그널을 보내게 된다면 저희가 계산을 할 때는 디퍼런셜 또는 커먼 모드로 좀 계산을 해서 이제 볼테지나 벨로시티 이런 거 모든 걸 보게 되는데, 그럼 저희가 처음에 설계를 할 때 원하던 V1, V2를 구하기는 어렵다라는 생각을 가질 수 있습니다. 하지만 실질적으로 이 두 가지가 서로 연관관계가 있기 때문에 저희가 오드 모드 또는 이분 모드만 해석을 한 후에 저희가 실질적으로 원하는 V1, V2를 손쉽게 계산할 수 있다는 것을 확인을 했습니다.
네, 이런 방법이 이제 수학에서 많이 사용되는데 이게 이제 리니어 시스템이니까 이렇게 되는 거죠. 세상에 좋은 사람이 있고 나쁜 사람이 있다. 조선 사람의 특징을 잘 또 해석하고 나쁜 사람의 특징을 다 해석한 다음에 좋은 사람 몇 명에 나쁜 사람 몇 명이냐 그거 곱해가지고 더하면 세상 일을 다 볼 수 있지 않겠냐 하는 게 이제 이런 거죠. 근데 실제는 꼭 그렇지 않죠. 세상과 좋은 사람으로 덧셈으로 되는 게 아닌 난리네하죠. 인간사가. 좋은 사람이 하고 나쁜 사람이 분리되는 게 아니라 좋은 사람과 나쁜 사람이 같이 있다면 서로 영향을 받잖아요. 그죠? 거기서 얘기하는 우리 여기서 얘기한다는 게 이제 모드 컨버전이 막 일어나는 건데 그렇습니다. This is the end of my class today. So the major target of my class today was to give you the basic concepts of differential mode and common mode. On Wednesday, I'm going to talk about generation of differential and common mode and propagation and deflections. It is a little bit more complicated compared to the single end line case, but let's enjoy that. Why do we, in the PCI Express, HDMI, USB, and serial ATA, why we are using differential scheme? Because to send really high-speed signaling to reduce the EMI, we really need the virtual ground plane. And without virtual ground plane, we will never be able to send high-speed digital signal from one to the other. So that's why we are spending here. Probably next Monday, we are going to talk more about the mode conversion and mode controls. And I'm going to spend more time on common mode case. And common mode is really problematic in many cases. Thank you for your attention. 동열, whose lab are you in?
저희 그 안승현 교수님 연구실에서 박사과정 재학 중에 있습니다.
그렇군요. 너무 쉬웠는가 보네. 강의 이렇게 설명드리는 거 보니까. 근데 쉬워도 상관없어. 기초가 탄탄하고 개념을 가지면 복잡한 문제도 꼭 블럭블럭 쌓아가면 이렇게 다 이해할 수 있고, 근데 꼭 블럭블럭이 기초가 든든하지 않으면 복잡한 문제 하면서도 하긴 하는데 좀 자신이 없거나 또 문제 봉착했을 때 그 푸는 힘이 약하게 되는데, 여러분. 자, 그래서 지난 시간까지 우리 계속 싱글 엔드 라인을 쭉 해왔는데 이번에 디퍼런셜 라인으로 가도록 하겠습니다. 이 디퍼런셜 라인 끝난 다음에 또 크로스톡 문제, 또 ISI 문제 이렇게 한 번씩 가보겠습니다. 오늘 아침에 조교가 여러분들 텀 프로젝트 다 리스트 보내왔는데 다 좋은 주제 같습니다. 여러분들 꼭 뭐 학점이나 이런 거 입장보다는 그냥 한번 수업에서 배우고 공부하니까 자기의 일어나는 시그널 인테그리티 문제를 한번 해석해 보면 어떻는가 싶습니다. 예, 여러분 수고 많으셨습니다. 다음 주 수요일 날 뵙겠습니다. 수요일 날은 또 조금 더 재밌게 해보겠습니다. 예, 감사합니다.